Hello everyone and welcome back to some more remote learning. In today's video, we're going to introduce the derivative through a couple example problems. So if you remember a couple worksheets ago, before we really got into how to evaluate a limit, we introduced the secant line and how that relates to the tangent line. If you remember, in order to find that tangent line, we first found some secant line and slowly got closer and closer to the value where we wanted to find that tangent line. It was kind of like we were taking the limit of the slope of the secant line to get the slope of the tangent line. But we did it through looking at the graph and through doing a table method. However, in this worksheet, we're going to do it by solving the limit now that we know how to work with limits. But again, let's review how we get that tangent line slope. So let's go back to finding the slope of the tangent line now that we know how to evaluate limits. So if we're looking at this first picture over here, we have some tangent line, which I made as this black dashed line at the point 1, 2. Now remember, in order to find a slope, what do we need? We need 2 points to find a slope. So if we want to know the slope at one single point and it only touches the function at that point, well, we're going to need to use limits to get there. So let's start by first creating a slope we do know how to calculate, a slope of a secant line. So you can see in this very next picture, I have a secant line that intersects the point 1, 2 and the point 2, 3 on the function. How do I find that slope of the secant line? I do f of 2 minus f of 1 all over 2 minus 1. My function value at 2 is 3. My function value at 1 is 2. So this is going to be 3 minus 2 over my x values, 2 minus 1. So this happens to be 1 over 1, which gives me a slope of 1. Although I'm not going to go very in-depth with this since we already worked through that tabular method on the example worksheets before we got into limits. But I want you to pick up on this pattern. So this is one slope of the secant line. Let's go down to our next picture. In our next picture now, we're looking at, well here, that purple function was our previous secant line. Now this green function is a secant line, but notice that that slope is even closer to our tangent line. So the slope of that secant line is, well, the x value for that new point is 1.5, so I'm going to find the function value at 1.5, and I'm going to subtract my function value at 1, and I'm going to put that all over 1.5, that x value, minus 1. So you can see this is going to be 2.75 minus 2, which is going to give me 0.75, over 1.5 minus 1, which is going to give me 0.5. 3/4 over 1/2 is going to be 6/4 or 3/2. So now I have a slope of 1.5. So my slope is even steeper. But like I said, I'm not too focused on that value. So let's move on to the next one where we get even closer to that x value. In the next one, we're looking at this orange secant line. So we're going to have f of 1.25 because that's the x value and I want to do my change in y. So I have to find the function value. So f of 1.25 will be 2.438, and then I'll subtract f of 1, which we know is 2, and that'll be all over 1.25, that x value, minus 1. 2.438 minus 2 is going to be 0.438, so we'll have 0.438 over 0.25. Doing that on a calculator real quick, I get 1.75. So I'm even closer to that tangent line, but I'm not quite there yet. But look what's happening. One thing is staying constant in all of these formulas, and that is my f of 1 and my point 1. 1 f of 1. That point is staying constant. Let me zoom out so you can see that other secant line slope. That point that's getting subtracted each time for both y and x is the same. The only thing that's changing is how my x values start farther away and they continue to get closer. So it's that 2 f of 2 that changes to 1.5 f of 1.5, which changes to 1.25 f of 1.25. We're getting closer and closer to that slope. So let's use this information and take the limit to find the exact value of that slope. So the derivative of a function is the slope of the tangent line anywhere along that function. And in this video, we're going to work at finding the derivative at a given point. So to find that rate of change at the point, we have the general definition f prime of a equals limit as x approaches a of f of x minus f of a over x minus a. Here is that change in y over the change in x. This f of a minus a remains constant, and as we move closer, this x is approaching a. Those are the values that are changing. So let's go ahead and now use this definition to do example 1. And let me reiterate real quick that all my slopes up above were the slope of the secant lines. So if this is the slope of a secant line, as I take the limit of it, that's going to be the slope of my tangent line. And that's the slope of my tangent line at the point A. F prime of A, that is the derivative at point A, otherwise known as the slope of the tangent line at point A. So let's now use this to solve for example 1. Now that we understand limits, we can do this. So we're going to, let me go ahead and zoom in, we're going to find the equation of the tangent line at x equals 1, where f of x equals negative x minus 2 squared plus 3. From this worksheet, my x, or my a value, is equal to 1. So I'm looking for the derivative at the point 1. And once I find that derivative, because that derivative is the slope of my tangent line, I'll be able to write that equation. And in order to write the equation, I need a slope and I need a point. So let's do the easy part first. Let's first find that point. So in order to find the point, I'll label that we're finding the point now. All we need to do is plug in our a value. So plugging in 1 into our original function will give us x comma y. So we're going to do f of a, which is going to be f of 1, and that's going to be negative 1 minus 2 squared plus 3. 1 minus 2 is a negative 1. Negative 1 squared is a positive 1. So we have negative 1 plus 3, because that negative was squared, but I still have that negative out in front. So negative 1 plus 3 is going to be a positive 2, which, hint, this is the graph from up above. So we're at the point 1, 2. That's the point where we're trying to find the equation of the tangent line. So you can see, so there's the graph of that function, negative x minus 2 squared plus 3. And here's my point that I'm trying to find that tangent line of, the point 1, 2. So it makes sense when we plug in 1, we get 2, and we can double check from our graph. So now I'm going to find the derivative at a. So I need to calculate the slope of my tangent line. And in order to calculate that, I'm going to find f prime of a, which is going to be f prime of 1. What I'm going to do is everywhere I see an a in this formula, I'm plugging 1 in. So I'm going to take the limit as x approaches 1 of f of x minus f of 1 all over x minus 1. Now, look, this is what I had circled up above. This f of 1 and 1 never changed, whereas my x, f of x, did. Now I won't be able to solve my limit yet because I need to plug my function in. So let's plug our function in and then simplify to solve. So we're going to have the limit as x approaches 1 of f of x, which is negative x minus 2 squared plus 3 minus, I know what f of 1 is, f of 1, we got as our function value of 2. When we're at 1 in the x, our function is at 2 in the y. So then I'll subtract 2, and that's all over x minus 1. Now, when we take the limit, we can't just plug x in, because if we plugged 1 in for x, we're going to get 1 minus 1, which gives us a 0 in our denominator. So in order to calculate this limit, we're going to try to get that denominator to cancel out. Let's use those limit methods that we used previously. And the way to start is by simplifying. So I'm going to have the limit as x approaches 1 of negative x minus 2 squared. But you know what I'm going to do? I'm actually going to expand that out. So negative x minus 2 squared is going to be a negative x squared minus 4x plus 4. And then I'll add that to, 3 minus 2 is going to be a positive 1. And that's all over x minus 1. I still can't quite cancel out this x minus 1, so let's continue to simplify until we can. So we're going to have the limit as x approaches 1 of, distributing that negative through, I'm going to have negative x squared plus 4x minus 4 plus 1 all over x minus 1. Now I can combine my negative 4 and my positive 1 to give me a negative 3. Now it's kind of hard to factor this with the negative distributed throughout, so let's pull that negative back out in front. So I'm going to pull my negative back out in front, and when I do, my signs are going to change. So pulling my negative back out in front, my negative x squared goes back to the positive. Where my 4x was added, it now becomes negative again, and then this 3, which was subtracted, will become a positive. So again, all I did was pull my negative back out of all of those, because it's easier to factor without it involved. So I'm going to have the limit as x approaches 1 of, how do you factor this? X squared minus 4x plus 3. What multiplies to give me a positive 3 and adds to give me a negative 4? That's going to be negative 1 and negative 3. So it factors into negative x minus 1 times x minus 3, and that's all over x minus 1. And look what can happen now. Now our x minus 1 cancels out, so that we can now indeed plug in 1 for x, because it no longer gives us something that's undefined. So our limit is going to be equal to negative 1 minus 3, which 1 minus 3 is a negative 2. Negative of a negative 2 is going to be positive 2. So our slope is positive 2 in this case. So if we have a slope of 2 and a point of 1 comma 2, let's write that equation for the tangent line. Y minus y1, 2 equals m, our slope of 2, times x minus x1 of 1. And there we have it. That's the equation of our tangent line for our function at x equals 1. And we can double check that slope since I have it graphed. Let's look. For every 2 in the rise, we go over 1 in the run. That is indeed the slope. Looking at that black dashed tangent line, every 2 we go up, we go over 1 in the run. Moving on to example 2, let's get some more practice with using that limit. So if we're trying to find the slope of the tangent line, or the derivative at the following specified a values of those given functions, let's go ahead and use that limit formula. Our derivative at a, our derivative at negative 3 is going to be equal to the limit as x approaches a, so as x approaches negative 3, of f of x minus f of a, so f of negative 3, all over x minus a negative 3, so x minus a, x plus 3. So I need to plug in my function, and I need to plug in the value f of negative 3. Let's first calculate f of negative 3. And let's go ahead and zoom in. So f of negative 3, when I plug negative 3 in, 6 times negative 3 is a negative 18. And when I subtract 7, I'll get a negative 25. So that's what I'm going to plug in for f of negative 3, and I'll plug my function in for f of x. So we're going to rewrite this as the limit as x approaches negative 3 of 6x minus 7 minus a negative 25. Subtracting a negative, same as adding that positive. So let's add 25, and that's all over x plus 3. Now, we can't plug negative 3 in for x because that's going to give us a 0 in our denominator, and we do not want our function to be undefined. So let's manipulate it. Combining negative 7 with 25, you can see that negative 7 plus 25 is going to give me a positive 18. So I'm going to have the limit as x approaches negative 3 of 6x plus 18 all over x plus 3. And what can we do? Well, 6x plus 18, we can pull a 6 out of every term in our numerator. So we're going to have the limit as x approaches negative 3 of 6 times x plus 3 all over x plus 3. You can see when I pull that 6 out of 6x, it becomes just an x. And when I pull 6 out of 18, it becomes a 3. Now, look what happens. That x3 cancels out to leave me with 6. So my derivative at the point x equals negative 3 is 6. So the slope of my tangent line is 6 for my function 6x minus 7 when I'm at an x value of negative 3. Let's go ahead and calculate the derivative of b at an a value of 1. So let's plug it right on into our formula. We're going to have f prime of 1, f prime of a, equals the limit as x approaches a, which is 1, of f of x minus f of a, f of 1, all over x minus a, x minus 1. Now we know what to do. We're going to figure out what f of a actually is, and we're also going to plug in f of x. I'm going to say is equal to the limit as x approaches 1 of 2x cubed minus 4x plus x, that's my function, minus f of 1. If I plugged 1 into this equation, f of 1, let me do this in a different color so you can see that I'm finding my point value, or my function value at a equals 1. F of 1 is equal to 2 times 1 cubed minus 4 times 1 plus 1. 2 times 1 cubed is 2, minus 4 plus 1 is going to leave me with a negative 1. So when I'm at an x value of 1, I'm at a y value or a function value at negative 1. So when I subtract a negative 1, that's the same as adding a positive 1. And this is all over x minus 1. Now I can't plug 1 in because that would give me something undefined. So I'm going to simplify and attempt to cancel out that factor in my denominator. So the limit as x approaches 1 of, I'll have 2x cubed, and I'll combine my like terms, minus 4x plus x is going to give me minus 3x, and then I'll have plus 1, and this is all over x minus 1. Now, is x minus 1 a factor of my numerator? I know that this is a polynomial, and I'm not undefined anywhere on that function, so I should be able to take the derivative and find the slope at any point. So I know for a fact that my x minus 1 is going to cancel out. But it's a little hard to think off the top of my head how to factor that numerator. 2x cubed minus 3x plus 1. I don't have an x squared anywhere in there, and I have some coefficient out in front of my highest degree. But remember, this represents division. Let's do some polynomial long division to see if we can simplify that fraction down a bit, and then maybe try to factor. So doing some polynomial long division, x minus 1, we're going to take that 2x cubed minus 3x plus 1 and divide by x minus 1. Now, in order to keep things straight, what I like to do is I like to leave room for all of my different degrees. So I actually have a 0x squared here because I don't have x squared in, and then I'll write minus 3x plus 1. It just helps me keep everything in line, kind of almost like a placeholder. So I ask myself, how many times does x go into 2x cubed? X goes into 2x cubed, 2x squared. 2x squared times x is 2x cubed. 2x squared times a negative 1 is going to be a negative 2x squared. And remember, I'm subtracting all of that. So my 2x cubed minus 2x cubed goes away, and my 0x squared minus a negative 2x squared is going to be a positive 2x squared. And I still have my minus 3x and my plus 1. Now I can continue with this polynomial long division, or I can just stop and rewrite my fraction here, because I can now finally factor. I can factor 2x squared minus 3x plus 1. That's something that's easy to factor. So I'm going to rewrite my limit as the limit as x approaches 1 of, I got a whole 2x squared, and then I'm going to add that to my remainder of 2x squared minus 3x plus 1 all over x minus 1. So now I'm taking the limit of this. And it may look messier, but my goal is to get this denominator to cancel out because I can't plug in a value of 1. I can plug in a value of 1 for that, sure, but I can't plug in a value of 1 for my denominator. So now I'm going to factor that new fraction I created. So this is going to be the limit as x approaches 1 of 2x squared plus, factoring that numerator, if I have 2x squared minus 3x plus 1, that's going to be x minus 1 times 2x minus 1. And that's all over x minus 1. Now, if you have trouble factoring that, I'm going to take a quick break directly after this problem and show you a factoring by grouping method. So feel free to skip over that if you knew exactly how to factor this. But look what happens, my x minus 1 cancels out. Now I'm able to plug 1 in everywhere in my limit. So my solution is going to be plugging 1 in for x, 2 times 1 squared plus 2 times 1 minus 1. That's going to leave me with 2 plus 2 minus 1 is 1. That's going to be 3. So my derivative of my function at the point when x equals 1, that slope of the tangent line is a positive 3. And quickly, as promised, that factoring by grouping method, here we go. If I have 2x squared minus 3x plus 1, I need to see what multiplies to give me a times c and adds to give me that negative 3. So 2 times 1 is 2. So my factors of 2 that add to give me a negative 3 are going to be negative 1 and negative 2. So I'm going to rewrite this negative 3x as a negative x minus a 2x, or a negative 2x minus an x. Either way of writing it is fine, and you're going to get the same result. So now I'll have 2x squared minus x minus 2x plus 1. So I just rewrote my polynomial, splitting up that negative 3x. But negative x minus 2x is still that negative 3x. It's still the same thing, but now I'm going to group my first two terms and my last two terms. So when I group those two terms together, I'm going to pull out the greatest common factor of each. So in this first chunk, my greatest common factor is x, so that leaves me with 2x minus 1. And I want to have this same exact result over here. What do I need to pull out? I need to pull out a negative 1. So if I pull out a negative 1 from negative 2x plus 1, that's going to leave me with 2x minus 1 inside. So you can see, so I have x times 2x minus 1 minus 1 times 2x minus 1. If I pull a 2x minus 1 out of each of these terms, then I'll have 2x minus 1 times an x minus 1. So you can see I pulled out 2x minus 1 from both of those, and it left me with x minus 1. And that's how you factor by grouping. I actually have a couple videos available, so feel free to check those out if you need more practice. So when finding the derivative using these limit formulas, a lot of it is algebra. Now that you understand how the limit works, it's really all algebra from here, so practice that algebra. Refresh yourself up on factoring, polynomial long division, completing the square, multiplying by conjugates. Practice up on that before you really dive into this worksheet, because it's going to make it so much easier. But for now, let's continue on to learning another definition for it. So the slope of the tangent line at a point, f prime of a, the derivative at a point, we can write as, well, we already know one formula for it. That was f of x minus f of a all over x minus a. That was equal to f prime of a. Well, f prime of a, we can also write taking the limit as h goes to 0. So as opposed to taking the limit as x approaches a, as x approaches a, that denominator gets closer to 0. So essentially, we're going to replace that x minus a. That's going to be now h. So replacing x minus a with h, our denominator is now h. So when we have f of x, well, x is really h plus a, or a plus h. So I'm going to have f of a plus h minus f of a all over h. So now I no longer am using that x variable, I'm using h's. And again, the only difference is I am making this change of x as it approaches 0, as that change of x goes towards 0, and I just need to adjust my numerator accordingly. So now my new formula I can use is f of a plus h minus f of a all over h. The limit of that as h approaches 0 is still f prime of a. So this is still finding the derivative at that point a. It's just another method to use. So now, as opposed to having to cancel out a factor in the denominator, all I have to cancel out is this single h term. So sometimes it's more advantageous to use this formula than the other, but as long as you practice and are comfortable using either, you'll be able to find that slope of the tangent line. So let's go ahead and practice with this new formula, and we're going to find the derivative of the following functions at the specified a value. So my f prime of a, my f prime of 2, for example 3 part a, my a value is 2. Using this formula, I'm going to take the limit as h approaches 0 of f of a plus h, so that's f of 2 plus h, minus f of a, f of 2, all over h. Now that we've got that formula down, let's go ahead and zoom in and manipulate it. What I'm plugging in is now I'm not just plugging in my function, I'm plugging in my function of 2 plus h. So this is going to be equal to the limit as h approaches 0 of, I'm plugging 2 plus h in for x. So this is going to be 1 over 2 plus h plus 1. You can see that 2 plus h got plugged right on in for x. So f of 2 plus h is 1 over 2 plus h plus 1. And I'm subtracting my function value at 2, which if I plugged 2 in for x, that would be 1/3. And this is all over h. Obviously, I can't plug 0 into my denominator because that's going to be undefined. So we're going to manipulate this in order to get that h to cancel out. So I'm going to have the limit as h approaches 0 of 1 over 2 plus h plus 1 is going to be 1 over 3 plus h. And I'm going to be subtracting 1/3, and that's all over h. let's go ahead and find a common denominator among my numerator so that I can combine that fraction that's in my numerator. So finding that common denominator, I'm going to multiply my first fraction by 3 over 3, and I'm going to multiply that second term by 3 plus h over 3 plus h. Now watch what happens as we simplify. This is going to give me the limit as h approaches 0 of, remember, our goal for these limits is to get that denominator, whatever is making that denominator 0, to cancel out. So when we used our previous formula, we wanted x minus a to cancel out. For this, we want that h to cancel out. So if we can get h somewhere in our numerator that's multiplied to absolutely everything, check, we're set, cancel it out, plug it in. Combining my two fractions in my numerator under that common denominator, I'm going to have 3 minus 3 plus h. And remember that 3 plus h needs to be in parentheses. If you drop those parentheses, you're not going to get the correct answer. So make sure you're using those algebra skills. And that's all over my common denominator of 3 times 3 plus h. So there's my numerator, and remember that's all over h. Or sometimes as opposed to dividing by h, it might be easier to keep everything in line by multiplying by its reciprocal. So dividing by h is the same as multiplying by 1 over h. I still can't plug h in because if I do, I'll get 0 in my denominator, and 0 times my other denominator will still be 0. I just rewrote this to keep everything kind of in line. So now, simplifying this, the limit as h approaches 0, 3 minus 3 plus h, well, my 3's will cancel out to leave me with a negative h all over 3 times 3 plus h, and remember that denominator is multiplied by h. Look what happens. I can now cancel out that factor in my denominator, that h, that was giving me an issue. I couldn't plug in 0 because I'd get 0 in my denominator, but once I cancel that out, I can. So plugging in h of 0, that's going to give me negative 1 over 3 times 3 plus 0, which is going to give me a negative 1/9. So negative 1/9 is my solution for part A. And what I mean by solution is that my derivative, or my slope of my tangent line, equals negative 1/9 for my function when I'm at the point where x is equal to 2. Now let's move on to part B, continuing to practice with this new formula that we learned. So I'm going to find my derivative, f prime of a, which is f prime of 1. So that's going to be the limit as h approaches 0 of f of a plus h, so f of 1 plus h, minus f of a, f of 1, all over h. So that's the limit as h approaches 0 of f of 1 plus h is going to be 4 times the square root of 1 plus h plus 2. That is my f of 1 plus h, plugging 1 plus h in for x, remembering how those functions work. And then minus f of 1. If I plugged 1 in, the square root of 1 is 1. 4 plus 2 gives me 6. And that's all over h. Now it's just a matter of simplifying this down and canceling out that h in my denominator. So I'm going to have the limit as h approaches 0 of, well, in order to simplify this numerator down, I can take this 2 and subtract 6. 2 minus 6 is going to give me a negative 4. So I have 4 times the square root of 1 plus h minus 4, and that's all over h. Now just to save me from having to rewrite this, I'm going to go ahead and pull out my greatest common factor of both my terms, which is 4 in my numerator. So when I pull that out, I'll have 4 times the square root of 1 plus h minus 1 all over h. So we got the square root, and we have that h in the denominator that still won't cancel out. What do you think we're going to do? Multiply by the conjugate. That's a good first step to take. So I'm going to multiply by the conjugate so I can get that square root out of my numerator. So I'm going to multiply by the square root of 1 plus h plus 1, because that's the conjugate, switching that sign, all over the square root of Well, I have to multiply by 1, so I'm going to write that same exact thing. The square root of 1 plus h plus 1. So when I multiply by this, let's see what happens. I'm going to have the limit as h approaches 0 of 4, all multiplied by, if I multiply the square root of 1 plus h times 1 plus h, that's going to be 1 plus h, and then minus that square root, but plus it again because I have that negative 1 and the 1, so that cancels out, and the negative 1 times 1 will be a negative 1. And that's all over. I'm not even going to worry with distributing that denominator out because remember, I'm trying to cancel this h out, so I don't want to put it in with all my terms. I want to leave it as is. So I'll have h times the square root of 1 plus h plus 1. Look what happens. This 1 cancels out with this negative 1, so I have h in my numerator that's multiplied to everything else in my numerator. So let me rewrite this to show you that it's going to cancel out. The limit as h approaches 0 of 4h all over h times the square root of 1 plus h plus 1, because this h is multiplied by everything in the denominator and this h is multiplied by everything in the numerator, I can cancel those out. And now I can plug 0 right on in for h because I no longer have a denominator equal to 0. So I'll get 4 over the square root of 1 plus 0 plus 1, which is going to be 4 over the square root of 1 plus 0 is the square root of 1, which gives me 1. 1 plus 1 gives me 2. 4 halves is what my limit is equivalent to, which gives me a value of 2. So my slope of my tangent line at my point x equals 1 is going to be 2. That derivative when a equals 1 is 2. Now just to get a little bit more practice in, we're now going to find the equation of the tangent line again. We're going to use this method with h, and we're going to find the equation of the tangent line f of x equals x squared plus 4x minus 3 at x equals 0. And in order to write the equation of the tangent line, we need the slope of the tangent line, which is the derivative, and we need that point. So let's find that point first. F of 0 is going to be 0 squared plus 4 times 0 minus 3. So f of 0 equals a negative 3. So our point is 0, negative 3. Now all we need to do is find the slope and plug that slope and point into point slope form to get the equation of our tangent line. And that slope we're going to calculate by finding f prime of 0. So that's the limit as h approaches 0 of f of a plus h, 0 plus h, minus f of a minus f of 0 all over h. Well, it's kind of nice that x is 0 and we found that point first because we'll just start plugging things in. The limit as h approaches 0 of, if we have f of 0 plus h, that's f of h. So I'm just going to plug h in where I see my x's. So I'll have h squared plus 4 times h minus 3. And if I'm subtracting f of 0, that's subtracting that negative 3. So adding 3. That's why I said it was nice that we found our point first, because that is f of 0. And then that's all over h. Remember, my goal is to cancel out h. And look what happens. We barely have to simplify this down. Negative 3 cancels out with 3. And I have an h multiplied by everything in my numerator. So my limit as h approaches 0, if I pull that h out so you can see, h pulled out of h squared plus 4h will leave me with h plus 4, and that's all over h. My denominator does indeed cancel out, or at least that part in my denominator that equals 0 cancels out. Now I plug 0 right on in to give me 0 plus 4, which is 4. So I have a slope of 4 and a point of 0, negative 3. Let's write that equation of the tangent line. Y minus y1, so that's going to be y plus 3 equals our slope of 4 times x minus x1, x minus 0. And for fun, let's simplify this down and write it in slope intercept form. So that will be y equals 4 4x minus 3. Distributing that 4 to 4x minus 0, which is 4x, and then subtracting this 3 on over. Looking at our function, when we're along that polynomial at the point 0, so at that point 0, negative 3 on our function, that tangent line is 4x minus 3. And with that, we wrap up this Introduction to Derivatives worksheet. Hopefully from this worksheet, you got some great practice of taking the limit of the slope of the secant line, and as we took that limit, you found the slope of the tangent line, which is the derivative. Now, when we continue on to our next example video, we're going to talk more about the derivatives, but let's just think on this for a second. If I wanted to find the derivative at x equals, now let's say 1, what am I going to have to do? Well, with the method I know, I'm now going to have to plug in all my new a values and solve. So I'm going to have to redo all of this limit stuff in order to figure out what that slope of the tangent line is at x equals 1. However, in the next video, I'm going to show you how to find the derivative, not just the derivative at the point. So once we find that derivative function, all we need to do is plug in our different point values as opposed to retaking the limit every single time. So this is going to make finding derivatives at different points along the same function a lot easier. So continue on to that next video, but until then, good luck with your online learning.